Today's lesson is going to be almost like a consolidation lesson of sketching graphs that have dilations, listing dilations, and um, interpreting dilations, I suppose, as well. So that's the name of the game. I'm hoping to give you at least half an hour on just practice from a whole bunch of exercises. There's a couple of scenarios I want to just throw at you first to make sure that you're okay with it. And I guess I'm going to put this in the basket of when is it not worth converting a horizontal dilation, a dilation in the direction of the x-axis, into a vertical dilation. So we've seen something like this where we've got y, sorry about the color there, a bit weird, try that again, like y is equal to, I don't know, 3x plus 6 cubed. And I said, rather than deal with the 3, we should take 3 out as a common factor. Should always do that, really. And then we know what 3 cubed is, right? 3 cubed is 27. So it's 27 outside of x plus 2 all cubed. That makes sense, I think. It gets rid of a horizontal dilation, then we don't have to worry about it. And secondly, it's going to be easier to sort of deal with overall. But when is it not reasonable to do it? With polynomial functions, that means something which is raised to a positive integer power. I think almost always it's worth doing. There's probably some scenarios where it's not, but it's almost always worth doing. But if we have something like this, it's always worth doing this, even if it gives you a yucky number. But the next thing is questionable. It's questionable to go, that's equal to the square root of 2 multiplied by the square root of x plus a half. You can do it. It's legit. It works. But to me, a horizontal dilation, a dilation in the direction of the x-axis by a factor of a half, that gives you a feeling, right, that it's kind of like squishing up the graph. So that kind of gives you a better sense of what's happening with the graph. Whereas a vertical dilation in the direction of the y-axis by a factor of root 2 is like a one now. Root 2 is what? How much? 1 point what? 4? Or is it 1.7? Or is it 1.3? It is 1.4 something. I can't remember. 1.41 something. It is that, but it's a lot less clear in your brain what that dilation is going to do. What is it? There we go. 0.414. That's the 3 decimal places or 4 significant figures. So although both of those steps are reasonable, I kind of feel like that's probably better for your thinking. So I guess as a level 4 student, what you're doing really is you're actually getting to the point where you need to make some executive decisions for yourself, rather than just being a bar lamb and following exactly the same process every single time. You need to step back and go, well, in this instance, I'm going to factor it out. In this instance, I'm going to factor it out because it makes my life easier. In this instance, it doesn't, so I'm not going to do it. And then, of course, there are other instances, like this one here. I'll just make it 1 minus 2x, where it becomes virtually impossible to do. I can take out a common factor of minus 2. You should always take out not a common factor, sorry. You should always take out whatever the value of the coefficient of x is. So that will give me minus 2 outside of minus a half plus x, or better written, the square root of minus 2 x minus a half. You should always do that. But then you can't take the minus 2 outside the square root symbol because of reasons we talked about last lesson, right? You can't leave the square root of a negative number outside the root sign. It just doesn't compute. It needs to be left in there. And again, that 2 there could be taken out, leaving the negative inside, but why necessarily create that work for you? It's probably easier to go, there is a reflection about the x-axis. There is a reflection about the y-axis dilated by a factor of 2, a half. with a translation to the right by half a unit. You see what I mean? So in this instance, it's better to leave it inside because you have to leave it. It's not even like you can take the negative outside the square root sign, and then having a root 2 on the outside, whilst legit, feels like it's making it more complicated. Any questions on that? Am I making sense? Yeah. So more cognitive load on you, right? Each time you pretty well much have to make a decision. On the other hand, if you had, say, y equals the square root of 4x minus 4, then taking out a common factor of 4 and then making that 2 root x minus 1, that kind of makes sense to me as well because it's a perfect square, so it's going to give us a nice little 2 on the outside. You may argue that it's probably best just to leave the 4 on the inside. I'm not adverse to that at all. It seems reasonable as well. But when I can do it easily, I tend to change my horizontal dilations to vertical dilations. You can't always do it, and it doesn't always make it easier. So only do it when it's easier. Questions before I move on? All right, there's one thing that I haven't exposed you to, which I'd like to do now. I've got a couple of examples written down so I don't lose my way. Almost exclusively, really, we talk about, when we're applying or listing transformations, we talk about going from a base graph into a new form of the graph, which is what we call an image. So we often say, list the dilations that take you from, say, 1 on x to 3 over x minus 2 plus 1, something like that. And you have to list the transformations. And the way I've taught you to do that is to list the dilations, reflections, and translations in that order, and make sure that you factor out a dilation if there is one here. There isn't one in this instance. So that's okay, except that it should be noted that you can actually transform any function into a different form of that function. We tend to go from the parent graph, but we don't have to. So, for example, I could say to you, this is so banal, it's not worth it. I could say f of x is equal to 3 on x minus 2, and g of x is 3 on x minus 2 plus 1. List the transformations that get you from f of x to g of x. There's one. You go up by 1 unit, right? Pretty easy. So you can go from any function to a new form of that function through transformations. It doesn't have to be from the base graph or the parent graph like 1 on x. However, it is a somewhat reasonable question to be asked in the exam to go all the way back to the parent or the base graph from a transformed graph. So you might be given this, and I'm going to go through a couple of examples with you. Yeah, I'll go through this. I'll go through a trunkus one to start with. It'll be like 5 outside of x minus 3 all squared minus 7, and you need to get it back to 1 on x squared, which is the base graph of a trunkus graph, yeah, or trunkus function. So this is probably going to not come as a surprise to you, but first of all, you factor out the any dilation of the x that's happening. We don't have any here. It's just x by itself. But if there was a 2 there, we'd factor out the 2. And then you list them in order, in opposite order. So instead of going dilation, reflection, translation, to go back to the parent graph, you're going to go backwards in your list. So you're going to list your translations first, then your reflection, then your dilation. Okay, to be perfectly honest, it doesn't really matter whether you do reflections or dilations in any order, but usually reverse alphabetical order is good. So for this one here, I would say, number 1, translate what? 3 units. I could have done the 7 first, but I'm going to do the 3 first. Translate which way? Yeah, good. I just heard a couple of people muttering left. Translate left 3 units, not right 3 units, which is what, if you're going this way, you would say this describes a translation right 3 units. Because I'm going this way, I'm saying in order to go back a step, I'd have to translate back 3. So I'd have to be adding 3 to this to get x squared by itself. So it would look like this. I'll just do it one step at a time just so that you can sort of see it. So when I do, so I start off with x minus 3 all squared minus 7. The next step would be to add 3 to the bottom. Okay, that's the translation left by 3 units, which would give me 5 over x squared, because minus 3 plus 3 is 0, minus 7. I won't do it for all of them, but does it kind of make sense what we're doing now? We're undoing what the transformation was effectively. So translate left 3 units, and then 2 is what? Have we finished with our translations? Nope, so we keep going. Translate what? 7 units what? Yep. It is down by 7, so we're going to go up by 7 units. And number 3, dilate by a, sorry, I always get this, don't put enough words into it. Dilate in the direction of the y-axis by 1 on 5. Well done, Darcy. 1 on 5, okay? Because 1/5 of 5 would bring it back to 1. Okay, so we've got to do the reverse of it. 1/5 of 5 will bring us back to 1. Does that make sense? I'm going to do one more example and then we're going to be done. Okay, no questions asked. You have to ask questions, otherwise I'm going to assume you're right to go. So I'm going to do this one here. Okay, so we've got y equals root of 10 minus 2x plus 1. And always, 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 our first step is to isolate out that reflection / dilation of x. So I'm just going to go straight for it, and you can ask me if you don't get why this next line is true. So I've changed the look of the function, but I haven't added or subtracted or multiplied or divided by it's the same function. I've just rewritten it. So minus 2 is taken out. I'm left with x minus 5 left over. Any questions before I move on? Awesome. So TRD applies. So step 1, are there any translations? Yaha. We've got 2 translations there. We've got to translate what? Yell it out, someone. Doesn't matter which order you do these translations. Yep. Translate down 1 unit. What's the next one? Yep, this is the Darcy show today. Oops, don't know why I said up. Yep, left 5 units. I always have to double check myself. Third one, there's 4 transformations. So what's the third one? You never dilate by negative, so you're nearly there. Dilation is definitely there though. Dilation in the direction of the x-axis. Yeah. There's that counterintuitive again, isn't it? By a factor of 2. By the way, it's never 2 units, it's 2. No, it's 2. Because we're going backwards, instead of being 1 on 2, it's going to be 2 on 1, which is 2. Does that make sense to everybody? Yep, okay, cool. Yes, he says in an impatient tone, fair enough. And the fourth one's pretty simple. Yep. About what? It was a 50-50. Yeah, it's the y-axis. Because it's inside the square root sign, it's a reflection about the y-axis. We're going swinging left and right like that. So that's how you do it, right? So if you're going to the parent function, you are going to effectively work your way backwards, TRD, reverse alphabetical order. Make sure that you do put it into this format already. Now, what I'm going to do now is I'm going to refer you to Google Classroom or to Sector, whatever you prefer, where the exercises for the day are to be located. What we're doing for the next half an hour or so maybe a bit longer, is that you're going to do a set of mixed exercises. It's all well and good to look at the individual functions in their own little right there and have a go at them individually. But I think it's more important for you to actually see a mixture of different functions so that you're constantly checking your own self and going, oh, this is the square root function. What does that look like? Or referring to your formula sheet if you need to, and keep checking yourself to make sure that you're applying the right properties. When it comes to sketching, it's always the same case, though. Think about it, what it looks like by considering the transformations. Put in the critical information, draw the graph. If you need to do one extra point for scale. If you've got enough points already drawn out, then you don't need the scale. That's basically it. All right, so I'll shut up. I'll stop this video and